Now you got connection. Go outside, yeah. Go.
Hello. So last time we finished talking about exoplanets, and today we are going to do the first of a two-part.
Go outside.
On Wednesday.
I'm in class.
The sun. So before I get started, are there any questions?
I'm in class. Go away. You. Give me your flip phone.
All right, so of course you're all familiar with
Give me your flip phone. I need hotspot.
But just like the moon, of course, it rises and sets every 24 hours due to the Earth's rotation. Right, and of course, also, right, the position of the sun against the celestial sphere. It moves around the celestial sphere once per year, right? That's because of the Earth's orbit around the sun. And remember, it goes above the ecliptic, and therefore in the northern hemisphere we have summer, and then goes below the ecliptic, and so for the northern hemisphere then we have winter. And that's due to the Earth's tilt. And today we're going to talk about just the sun itself, and we're going to see some cool pictures of the sun. So a couple things, right? The sun, one neat thing is it's the closest star to us. So what we now understand is it's just a star. And there are, of course, there are billions and billions of stars. It's a fairly normal star. It's about halfway through its lifespan. It's going to last about 10 billion years. It's about halfway through it. Detail about the
What the heck are you trying to do?
Later on, after spring break, we'll talk all about stars, and then you'll see how the sun fits into the general range of possible masses and temperatures, colors of stars, and so on. But a neat thing that because this star is so close to us, right, we can get some wonderful pictures. Some of the pictures I'm going to be showing you are actually due to an amateur astrophotographer. Alan Friedman has just a 10-inch telescope in his backyard in Buffalo, New York, and he takes some of the best pictures of the sun. So I'll show you some of those. Here's one. If you use a filter so that you only capture the hydrogen alpha lines, you reveal some really interesting structure on the surface of the sun. So here you actually see kind of a furry, almost surface, and we'll talk about that maybe on Wednesday.
Take it, go.
Details of activity on the surface of the sun. You also see over here some flares, we call them. And going back a little bit to history, of course, people for a really long time wondered what on earth the sun was, and they had no idea. We'll talk more about that today. But one interesting thing is that the Greeks, going back to Empedocles in the 5th century BC, supposed, incorrectly, but they supposed that all stuff we see around us were different combinations of only 4 things: earth, air, fire, and water. And one thing that's kind of interesting is that even though that was wrong, right, we now know that things are made of atoms, and there's 100 odd different atoms and so on. It is true, actually, that that they got basically right was that what we now call the 4 phases of matter. That is,
4 phases.
any type of matter can be a solid, typically when it's under high pressures or very cold. So think of ice, right? So water can become a solid when it's cold. Water can also become a liquid when it warms up, right? So it's another phase of matter is liquid. If you heat up, say, water more, it becomes steam, it becomes a gas. And you're all familiar with the air around you. That's an example of a gas. And then if you heat it up even more, you get a flame, and that's called a plasma. The difference between a gas and a plasma is very similar to a gas, but it's so hot that the electrons are removed from the atoms. They don't stay connected to the atoms, so you get these separate positive nuclei and negatively charged electrons all swimming together in kind of a gaseous soup called a plasma. And that's what happens in a lighter flame or a match flame. Okay. And so in this sense, they actually kind of got it right, the 4 phases of matter. And the sun is a plasma, okay? Sometimes I might kind of sloppily call the sun a gas because it's made mostly of hydrogen. We tend to think of hydrogen gas. But I'm going to try to at least say the correct thing, which is technically it's a plasma because it's so hot, it's hydrogen gas.
Shut up!
It's technically the 4th phase of matter, which is a plasma. So that's what the sun is. It's a plasma, mostly hydrogen gas or hydrogen plasma. And so if I were to ask you, what does the sun consist of? Gas, liquid, solid, or plasma? I want you to know it's a plasma. So we're going to be talking about the sun close up and all of its interesting features, and it's the only example of a star where we can do that because all the other stars are so far away. They're really just points of light. But it's kind of cool to do the opposite. That is, we've sent probes so far away from the sun that it now just looks like a star to them. So here's a wonderful picture from the Voyager probe that it took in 1990. It's past Neptune at this point, exiting the solar system, and swivels around and takes a picture of that captured the Earth and Venus and the sun. And you see the sun looks just like a star. And you can't really see it unless you zoom in here, but you have Venus, and actually this is a very famous picture where Earth is kind of suspended in one of these little beams of light. It's just a pale blue dot. That's where the phrase pale blue dot comes from this picture. But we can take these wonderful up-close photographs of the only star we can do this to is our sun. Here's another photograph by Alan Friedman's 10-inch backyard telescope, capturing also. So I'm trying to, if I give you a picture, I'm trying to make it interesting too. This one has a International Space Station crossing it right here. And then these features are sunspots. So the sun is not, it's this hot plasma that's active. There's things happening on the surface of the sun. Of course, it looks very round, but we're seeing it from very far away, and gravity pulls it into a sphere. But there are things happening on its surface. So we're going to talk about these. These are called sunspots, the regions where it's not quite as hot. So it appears in a photograph like this, it appears darker. I mean, it's still very hot, but it appears darker relative to the rest of the surface. It's much, much hotter. And then here's another one of these photographs where we add a filter. So this is looking specifically at a spectral line of hydrogen called the hydrogen alpha line. It's in the red part of the spectrum. And you reveal this even more interesting stuff going on the surface. So you see some evidence of sunspots. So here's one. Here's a sunspot. Here's a sunspot. We also see that the surface almost looks furry, right? Here you see at the edges some of these are flares, solar flares, regions where the sun is kind of burping out hotter plasma at those places. And it'll turn out that, as I said, the sunspots are colder places. And there's a reason for that we'll talk about, having to do with the tremendously powerful magnetic fields that interact with the plasma. That's one interesting thing about a plasma that's different from a gas, is that you have these charged particles in a plasma, unlike a gas that's neutrally charged. And because a plasma is charged, it interacts very strongly with magnetic fields. Here's a more up close. In this case, you're seeing some of this activity that we're going to be talking about, flares and solar prominences. And you also see kind of that furriness on the surface of the sun due to kind of patterns of how the ions in the plasma are following magnetic field lines. You see here sunspots. Here's another one. Really beautiful picture. You see that kind of texture to the surface. You see examples of sunspots here. You see examples of solar flares here. And here's an up close of sunspots. So what you see are these regions. Now, in reality, they're glowing, yellow hot. But whenever we take a picture of the sun, we have to put a filter on it to make it less bright. Otherwise, it would just burn our eyes and burn our film, right? So we put a filter on it so everything looks yellower, when in reality it's more white, right? And then in that case, the sunspots look dark, as though they're not glowing at all. But in reality, they're burning hot, right? But they are cooler than the rest of the sun's surface. And you also see this interesting kind of furriness, kind of looking like it's all pointing away from the sunspots. And as we'll learn, those are charged particles in the plasma following magnetic field lines that tend to connect to these sunspots. You're also actually beginning to see here what we call granules. This is like the fact that the sun's surface is like the surface of a pot of boiling water. And these are similar to what you see on a pot of boiling water. You see regions where the hot stuff is bubbling up from below. You're seeing these here. I'll show you a movie of these in a minute. These are called granules. And then in addition to some of these wonderful pictures from this backyard telescope, we also have some pictures from dedicated like NASA satellites. This is from the Solar Dynamics Observatory, catching what we call filament or coronal mass ejection. This is where the sun is basically burping out huge amount of super hot plasma. Okay, and it kind of forms a actual material that it's going to release out into space. We call it filament here. So before we go any further, we need to remind you about, right, how do things glow? The fact that the sun is glowing white hot is a fact that results from this law of black body radiation we've talked about a couple times now, called the Stefan-Boltzmann law. And the idea here is that anything with a temperature glows. You and I, we all glow, but we're at a low temperature, so we glow in the infrared part of the spectrum. And if you heat something up, it starts to glow more and more. And it starts to glow red, then yellow, okay, eventually blue, and then even it'll start to glow in the ultraviolet X-ray if you get it hot enough. And what the Stefan-Boltzmann law tells us is just the total amount of luminosity, meaning the total amount of light energy emitted, depends on two things. It depends on the area, the surface area of a star or anything, you or me could be talking about. So the larger an object is, the more light it emits. And two, its temperature. So the hotter something is, the more light it emits. So hotter stars emit more light. And then, as I implied, the hotter you are, you also start emitting different colors of light. So things at room temperature emit lots of infrared, right? So you can see me, say, through in a dark room, you can still see me in an infrared camera because I'm glowing in the infrared. Okay, but you heat something up, it'll start to glow red, and it'll glow yellow, and then blue. And that's what this shows. It shows that heat something up sort of hot. It's emitting a range of wavelengths, but the peak is red in this case. And you heat it up some more, the peak wavelength is shifting to the left to a smaller wavelength. So the wavelengths are on the x-axis, where the peak now is yellow. And you heat it up some more, and the peak now is blue. And you see also at the same time, the total amount of light is increasing. Okay. So if you heat something up, it starts to emit progressively shorter wavelengths of light or bluer colors. and it gets brighter. And this applies to anything that has some temperature, including stars. And so this is what we see when we look at the sun. We're looking at its surface. And that surface is glowing, some infrared, but also all the colors of the rainbow, and it has some peak corresponding to a temperature of the surface of the sun. Okay? And one thing we can use to learn the temperature of the sun, or vice versa, to learn the peak wavelength emitted by the sun, is this handy formula called by Wien, who discovered this law, the law that as you increase the temperature of something, it progressively emits shorter and shorter wavelengths of light. So this law says the wavelength times the temperature is constant. In other words, you increase the temperature, you decrease the wavelength. And so, for example, we can apply this to the sun's surface. The surface temperature of the sun is about 5,800 degrees Kelvin. It's pretty hot, okay? And if you use Wien's law, that means you plug in 5,800 degrees Kelvin here, and you plug in this constant, okay, and you solve for the peak wavelength. And what do you get? You get a peak wavelength of 5.02 times 10 to the minus 7. In other words, 502 nanometers. That's a wavelength, very small, less than the width of a human hair. That corresponds to the color green, okay? And that corresponds to also the peak sensitivity of the human eye. The human eye is most sensitive to green light, which isn't surprising because we evolved in the presence of the sun, where sunlight, the majority of it is green.
Mm.
So here is a comparison of the theoretical black body spectrum curve in gray, and the observed spectrum of light from the sun in yellow. And they're pretty much, they're very similar. And so what you see is that the sun emits a range of wavelengths of light. It emits some UV, so down here is ultraviolet. It emits some visible light, peaking in the green part of the spectrum. And it emits infrared out here. And in total, every square meter of space receives about 1,300 to 1,400 watts of light if you add all that energy up. Okay, so here's another kind of cleaned up picture here of that black body spectrum curve showing where the visible light is. So you see the peak is around green, and you see that about 40% of the sunlight is in the visible part of the spectrum. So in this region here, about 10% is ultraviolet, and about 50% out here is infrared. And remember, here on the surface of the Earth, on average, we only receive about a quarter of that 1,300 watts per square centimeter. That's because it goes down by half because of the day-night cycle. Half of the day, or half of every 24 hours, we're in darkness. And because of the fact that the Earth is curved, and you have that sunlight being spread out, diluted over a larger surface area. Instead of, if the Earth was flat, all that light would be concentrated in that direct line of sight of the sun, but instead you're spreading that same amount of energy over a larger curved surface. And together that means that on average about a quarter of that 1,300 watts hits the Earth's surface. And then finally, on the Earth's surface, you also have the fact that the sunlight is absorbed by the atmosphere. The atmosphere doesn't absorb much visible light. It mostly absorbs ultraviolet due to the ozone layer, and it absorbs infrared due to so-called greenhouse gases that we've talked about. The greenhouse gases mostly being water vapor and carbon dioxide. Okay, and so one thing I want you to get out of this is that the sun's surface temperature is about 6,000 degrees Kelvin. A little more accurately, 5,800 degrees Kelvin. But it's about 6,000 degrees Kelvin. And based on that surface temperature, we can calculate the same thing we observe, which is that the sunlight reaching us is mostly in the visible, well, it peaks in the visible part of the spectrum. Right? So if you ask which wavelength of light has the most amount of that light reaching the Earth's surface, it's in the visible. Any questions so far? So there's an interesting historical question. Right? Why does the sun shine? What even is the sun? And it's kind of remarkable that we've only really figured out what the sun is in less than the last 100 years. But maybe first correct hypothesis was maybe 80 years ago. Boy, I mean, no one knew. I mean, some people supposed that the sun was like other stars dating back a long time, but other people thought that the sun might be like a planet, like where you could walk on, like the moon. I mean, seriously, that's what people thought, like just like 120 years ago. And no one knew why the sun shined, right? So thinking about this, the solar luminosity, the total amount of light energy released by the sun, though, is incredibly high. It's 3.8 times 10 to the 26 watts. Now, to put that in perspective, that's about 10 trillion times world energy production. Okay? That's how much energy the sun puts out every second. Okay, and people have proposed at various times explanations for how something could put out so much energy. Anaxagoras, 500 BC, suggested that the sun was basically a big, pile of garbage on fire, big, wood fire, basically, right? A ball of fire. You can think about wood or coal or lamp oil, right? The problem is that doesn't work. Now that we know that the solar system is about 5 billion years old, if we had a pile of coal the size of the sun and had it emitting that much energy, it would burn up in only 10,000 years. So there's no way the sun could be made out of coal or gas or anything like that. So it has to be something very different that powers the sun. Another proposal made in the 1850s by Helmholtz and Kelvin, two names you've heard of Kelvin, that's the name of the temperature scale, but Helmholtz was also famous. They proposed that heat from gravitational contraction could power the sun. Now, this is actually a pretty good idea. So remember, since the formation of the nebula that our solar system came from, right? As it contracts, it heats up because that gravitational potential energy turns into thermal energy. And the same thing could be what powers the sun, right? It's still maybe contracting very slowly. That keeps it hot. And that actually works a lot better than a pile of coal. But still, if you calculate all that energy, it would only last the sun at its power output, could only last for 25 million years. So that's still more than 100 times less long than the sun has been alive. That still doesn't work. So finally, in the 1930s, we started to understand about nuclear fission, nuclear fusion. We figured out that what could power the sun? Nuclear fusion do it. Okay. If we calculate the energy in when you fuse two hydrogens together, well, when you fuse 4 hydrogens together to produce a helium atom, if you have a sun made of hydrogen and you keep doing that, it has enough energy to last 10 billion. And indeed, that's our modern understanding. The sun is about halfway through its life. In total, it's going to last about 10 billion years because it'll eventually run out of hydrogen. It'll exhaust its fuel source. And one way of thinking about where this energy comes from is the fact that the sun has a lot of mass. And what it's doing, and this is the way you get energy in nuclear fusion, is you're literally, and it's not figurative, you're literally turning mass into energy. according to Einstein's E equals mc squared. So here I'll let Einstein explain. So he says that it followed from the special theory of relativity. That's his theory in 1905, in which E equals mc squared. It followed from the special theory of relativity that mass and energy are both but different manifestations of the same thing. Furthermore, the equation E is equal to mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light. And this showed that very small amounts of mass may be converted into a very large amount of energy, and vice versa. Mass and energy were in fact equivalent, according to this formula. And then he says that this was demonstrated in 1932, and it's true. We can, in fact, nowadays we demonstrate this all the time at particle colliders like the Large Hadron Collider. We smash particles together and we literally turn energy into mass. And nuclear fusion does the same thing. Okay, if you look at a periodic table and you take the mass of 4 hydrogen atoms, and then you look at the mass of 1 helium atom, it's not the same. Some of the mass in those 4 hydrogen atoms had to go somewhere, because the mass of what it produces, a helium atom, when they fuse together, is actually less than the sum of the 4 masses. So that energy had to go somewhere. Where did it go? It went into sunshine. So literally, we're turning mass into energy. And here I got a number for you to give you a sense for just how much. The sun converts 4 million tons of mass into pure energy every second. So the sun is losing 4 million tons every second in order to power itself. Now, luckily, if you calculate it, that's only 0.00000000000002% of the sun's mass that it's losing every second. So that's not very much. So luckily, that if you do the math, that allows the sun to last billions of years. Okay, so on this page, I have an overview of the sun. It's 99.8% of the solar system's mass, right? So most of our, we talked about all the stuff in our solar system, but it's mostly the sun. And it's mostly hydrogen and helium in the form of a plasma. Right? It would be a gas, but it's very hot, so it's a plasma. It's about 108 times the size of the Earth, and it's about 300,000 times the mass of the Earth. And overall, its average density is actually similar to that of Jupiter. Its average density is a little bit more than the density of what? Now, as we'll talk about, the inside of the sun has a very high density, but the outside of the sun has a very low density. So on average, it's about the density of water. It's about 70% hydrogen, 28% helium, and then a couple percent heavier elements. And so I've talked a lot about the thing that powers the sun. So here I'll give you your first poll question, which is
Nuclear fusion.
for the past 4.5 billion years, the sun has generated energy through what?
What's you at 12:30?
Fusion.
You sure?
Reactions.
Go away. 12:30. Because it's not time yet. 12:30. Nuclear fusion, fusion, fusion.
Give you 10 more seconds.
Is it that?
Okay. All right, and most people got the correct answer. Nuclear fusion. That is actually what's happening is the sun is made of mostly hydrogen and helium. Well, you're fusing 4 hydrogen atoms into a helium atom. And in so doing, you lose a little mass, and that mass turns into energy.
Fusion, not
So are there any
fission.
questions for that so far?
Whew.
So we talked a little bit earlier about this proposal of Helmholtz and Kelvin that maybe gravitational contraction could actually power the sun. And that turned out to not be true. It could power the sun for only about 30 million years. And in fact, that's what happened in the first few million years of the solar system that led to it getting hot enough in the sun to start fusion. So if we go back to the beginning of our solar system, 4.5 billion years ago, the solar nebula was contracting, converting gravitational potential energy into heat, getting hotter and hotter, until the temperature of the sun reached about 10 million degrees Kelvin. And that's the temperature you need for fusion to begin. That's the temperature you need so that 4 hydrogen atoms snap together hard enough to create helium atoms. Okay. And that contraction eventually stopped, right? The sun doesn't just keep contracting into a black hole. It stopped when the fusion was able to produce so much heat that the pressure pushed back out, okay, to prevent further contraction. And okay, so stopping for a moment to give you an example of something I expect you to know. Roughly, what is the temperature you need to ignite fusion to happen in the sun? And this also conversely tells us about how hot it is in the center of the sun. It's about 10 million degrees. Remember, that's different from the surface of the sun. It's cooler out at the surface of the sun. Remember, that's about 6,000 degrees. But in the very center, it's about 10 million degrees Kelvin. And so you were just talking about how the sun doesn't contract into a black hole. The sun stays at relatively a constant size, although as we'll talk about, as it enters its end of life, it starts to expand. But if you think about it, nuclear fusion, that's the same thing that is used in thermonuclear bombs, right? The sun is like a giant thermonuclear bomb, atomic bomb. So why doesn't it just explode? Well, it's because gravity is so strong, right? So the sun literally is like a giant nuclear bomb going off, but gravity is strong enough to hold it, to prevent it from blowing outward. So it's actually in what we call equilibrium. That is, you have gravity pulling in is in balance with the pressure pushing out. Okay, the pressure as you go further and further in the sun goes up really, really high. At the center, it's about 200 times that of the pressure at Earth's 200 billion times the pressure on Earth's surface. So really, really high pressures in the center of the sun. And the idea is, right, so the sun, gravity wants to pull the sun inward, but the nuclear fusion is creating heat that causes it to billow back out, right? And that is in balance. Over the sun's history, it has changed size some. And that's because the total amount of energy produced by fusion has been changing a little bit. Basically, so first of all, since the sun began about 4.5 billion years ago, it's changed, it's increased in size just a little bit, about 20%, as the nuclear furnace at its core has gotten a bit hotter. And that has kind of pushed the surface out, equilibrium size out. In the future, actually, the sun is eventually going to expand into a red giant, which we'll talk about when we talk about the lives of stars in a couple lectures from now. But that's because, for reasons we'll discuss, it starts producing more energy in its core, and that'll push, that causes the surface to push out a little further. So this shows that as a star evolves, its luminosity, its brightness increases a bit over billions of years, and its size increases a bit over billions of years. By the way, the surface temperature shown in green stays relatively constant. So as you have this equilibrium where the temperature in the core is changing, or the amount of energy produced from the core is changing. It pushes out the surface a little bit until the temperature on the surface is about the same. Next, I want to talk about structure. Okay, some of the right, if we were to do a cross section of the sun, what's going on the inside? Okay, so we're going to kind of take a tour of the inside of the sun. Here's an overview, and we're going to go through each piece. And basically, the overview is you have a core, you have the radiative zone, you have a convective zone, and then you have the chromosphere and photosphere. And okay, on the surface of the sun here, on the photosphere, now you have features like these granules we'll talk about, these sunspots, you have these flares and prominences, and then outside that you have the corona. So we're going to go through each of these features. If we start in the very center, so I have kind of a cartoon where this here is the surface, or what we normally think of as the surface of the sun, right here. And we're going to start in the very center, which is the core, so what's shown in red. And this is all to scale. So it's about 20% of the size of the sun is, right, if you were to go out to the surface. 20% of that size is shown in red, and that's the core. And in the core, the pressure is incredibly high. So about almost 1 trillion times the pressure on Earth. The temperature is about 10 million degrees. The density is really high, right? All that pressure pushes the density to be about 8 times the density of gold. And this is where the nuclear fusion is happening, in this core. This is where the energy is all coming from ultimately, in this core about 20% the size of the sun. That's where it's hot enough for the fusion to take place. If we move outward into this yellow region, this is called the radiative zone. Okay, and this comprises perhaps the majority of the sun, so going up from here out to here. So here the density is changing. It changes kind of from the density of like a foam up through kind of the density, the density of gold, right, around the core, out to the edges of kind of the density of a foamy water. And this is the region where the energy is being transported from the core outward, right? And it's called the radiative zone because it's how the light is trying to escape through this really dense plasma. And the
What's up,
light
baby?
has
Sleeping? No, I'm still in
takes a
class.
very
What?
long time to escape. It has a hard time escaping through the radiative zone. It's so dense that the light keeps bouncing around, and it takes a very long time to get out. Okay. Next, finally, the light, it gets less and less dense until the light finally can escape. And this is called the convection zone, where instead of the energy being transported by light, the energy is mostly being transported by rising hot, billowing, rising hot plasma, where you have convection. It's called the convection zone because you have these hot bubbles of plasma rising up from the radiative zone, and then it goes up and it cools off and it falls back down. And it's a convection pattern, just like you have in a pot of boiling water. And that goes all the way out to the very edges of the surface of the sun. And in this convection zone, it has density roughly of air. And finally, you get to this region here called the photosphere. It's about 6,000 degrees Kelvin. This is the visible surface of the sun. It's only about 100 kilometers thick. It has a very low density, much, much lower than the density of air. Okay? The light just escapes out of the surface. It has this churning, so we'll see when we see pictures of the sun, this is what we see on the surface, the photosphere. And we see the churning, what we call granules, the evidence on the surface of all the rising hot plasma boiling up from below. After the photosphere, you have the kind of a chromosphere. This is like the part of the solar atmosphere. It's about 2,000 kilometers thick, and it actually gets hotter than the 6,000 degree surface. It actually rises to about 100,000 degrees Kelvin, and this is where most of the ultraviolet light comes from the sun, because it's hotter, right? Out at the region where it's hotter, it's mostly emitting ultraviolet light, And then even past that, we have the corona. The corona is the outermost solar atmosphere and extends out to about twice the size of the sun. So that's what's shown here. From here to here is the corona. And it's actually the hottest outside of the core, about a million degrees Kelvin. And it's so hot that it emits lots of X-rays. This is where most of the X-rays come from the sun. Finally, what's indicated by these dotted lines is that another thing you can consider part of the sun is its solar wind. It's constantly emitting a flow of charged particles from its plasma, emitted out into space. And actually, there's a region around the sun that's kind of like a bubble in which the solar wind, the wind from the sun, is pushing outward into the interstellar region. Okay, that region extends beyond Pluto. Okay, so here's just a quick overview of everything we talked about. You have going from out to in, you have the solar wind, the corona, chromosphere. All of these can be considered part of the atmosphere of the sun. You have the visible surface of the sun called the photosphere. Then inside the sun, you have the convection zone, the radiative zone. It takes about 100,000 years for light to get from the core out to the surface of the sun. And that's because in the radiative zone, the light keeps bouncing around. It takes forever. Well, it takes 100,000 years just to get out from the core, out to a place where it can kind of move more freely. Okay. So the light you see from the sun is light that was produced about 100,000 years ago. Okay, and then finally you have the core, where it's really dense, 10 million degrees. This is where you have the nuclear fusion happening that creates all the energy that the sun outputs. Here's a picture during a solar eclipse. That's the only time where you can really see the corona, that large outer atmosphere of the sun. It's very hot. It's a lot of X-rays, and you see it's rather beautiful. So you're seeing here the corona of the sun. It's normally kind of invisible because the sun's too bright for you to look looking at it. And then also speaking of the solar atmosphere, remember there's this interesting feature where the surface of the sun is about 6,000 degrees Kelvin. But as you go out into the solar atmosphere, it's getting much less dense, so there's less energy in it. But the temperature actually goes up. And you can see this if you just look at the sun in different filters. So here's just the visible light filter. So this looks like the normal sun surface right here. But you start doing filters, you see, okay, here's where most of the light from a 6,000 degree object is coming from. But then you start going up to tens of thousands of degrees and even millions of degrees, and you start to reveal parts of the corona. In other words, you can actually see, just by using filters on your telescopes, you can see the temperature variation in the sun's atmosphere. Okay, and when we look at pictures of the sun, you often see some of this kind of, it's not, depending on the filters used, it's not perfectly smooth on the surface, right? You see some sort of structure here. And what you're seeing evidence of here are what we call the granules and convection cells. That is, the sun's surface is like the surface of a pot of boiling water. It's covered in millions of granules, okay? Each one is like the size of the United States, okay? Really big, but they're convection cells. This is where hot, so if we look at this picture here, the brighter regions are where hot plasma is rising up through the convection zone, and then it cools off at the surface, releases all that energy, and then falls back down along the edges where it's darker because it's not as hot. Let's see. Yeah, so here's a picture of where someone's overlaid like the United States, just give you a sense of scale. And here I can actually show you, you can actually watch this churning, roiling surface of the sun in video taken. So here's one. These are actually really mesmerizing. It's a time-lapse photograph or movie of the surface of the sun. Remember, this is like the size of the United States, and it's like the surface of a pot of boiling water. You're seeing evidence of the hot plasma rising up from below, cooling down, getting darker, and falling back down along the tables. Okay, here's another, maybe slightly better video, but shorter. Isn't that beautiful? And you're looking at a sunspot there too. Play that again. Yeah, that's really beautiful. So the links are in my lecture. Okay, so that there you're seeing granules, which are the kind of the surface of these convection cells. Okay, and so now going back, so we just talked about the corona and the solar atmosphere and the photosphere, where you see those granules and convection cells. In the radiative zone, right, this is where it takes photons of light literally more than 100,000 years to get out through the radiative zone, out to the convection zone, so they can escape. Here, so at any time I make these lectures, I simulate a random walk, is what you call it, of photons. That is, the photon goes, a few hundred kilometers, and then randomly gets bounced some other direction, right? So it goes this way, and then it randomly gets bounced this way, and this way, and this way. And so it takes, on average, about 100,000 years for a given photon of light to escape. It just keeps getting bounced around in random directions anytime it tries to get any. So here I've simulated in different colors: 1, 2, 3, 4, 5 example photons. And so remember I said that it takes about 100,000 years for these photons to diffuse out through the radiative zone. So if you ever see sunlight from the sun, it's about 100,000 years old. So here, hopefully this is therefore a pretty easy question to answer. So one more poll question for you. The light radiated from the sun's surface reaches Earth in about 8 minutes, but the energy from this light was produced by fusion in the sun's core when?
700 to 1,000. I think it's D.
All right, I'll give you 5 more seconds. Okay. And yeah, most people got that right. So
the last one.
as I, took the time to give you the answer right before the poll, was about several 100,000 years.
Not
ago.
the several
So
thousand.
on average, about 100,000 years or more
Both
for
these.
light to get out of the sun. Are there any questions about that? So here's just in one single picture giving you an overview. Fusion happens in the core, radiative zone where it takes 100,000 years for light to escape. The convection zone, here's the visible surface called the photosphere. Just above the photosphere, you have a chromosphere that's not shown. That's the part of the atmosphere, but the majority of the atmosphere is in the corona where it gets very hot. And then you have a solar wind. one thing we've covered that I want you to know for sure is that the core of the sun, okay? The core of the sun is much hotter and much denser, okay, than its surface. Okay, the surface of the sun is relatively cool compared to the rest of the sun. So the surface is only about 6,000 degrees Kelvin. The core is 10 million degrees. It has to be hot enough for fusion to happen, right? The core is where the energy is being produced by fusion. And it's also very dense. A million times less dense than air. The core is 8 times the density of gold. Okay, and that's just because of the tremendous pressures in the center of something that large. It's remember the sun is way more massive, 300,000 times. It's another thing to know. 300,000 times more massive than the Earth, right? So of course the center is going to be under very immense pressure. And there you go. Another question, or the sort of thing I want you to know, right? What's closest to the temperature of the sun's core? About 10 million degrees. Right? And the other temperature I want you to know is the sun's surface. It's about 6,000 degrees. Okay, and I mentioned the solar wind, and you can really think of there being like a bubble around the sun that's filled with the sun's solar wind, and you can even consider that to be an extension of the sun's atmosphere. And so here's a picture, right? Here's our solar system. There's sun in the center. So here's kind of the edges of the solar system. And going out much further than that is this bubble where the solar wind from the sun starts to run into and push against the interstellar medium. That is, right, outer space in between stars is not totally empty, right? It has bits of gas, and that gas is pushed up against by the influence of our star. Okay, and this region is called the heliosphere, and it's kind of oblong shaped because the sun is moving relative to the interstellar medium. The sun is orbiting the center of the galaxy, and in this picture, the sun is moving to the right. So as it moves to the right, you have the interaction. It's pushing against the interstellar medium here. And the Voyager probe, that one of those ones that turned around and took a picture of the sun, which just looked like a star, and you saw that pale blue dot of the Earth suspended in a beam of light. These Voyager probes have exited that heliosphere, and therefore that's one definition of the solar system. They have exited the influence of our sun. Okay. So as of a couple of years ago, I haven't updated this, but they're about 150 times the Earth-Sun distance away. Okay, so this brings us back to an overview of the sun, right? It's 99.8% of the solar system's mass, mostly hydrogen and helium. That hydrogen is being turned into helium slowly. 4 million tons of mass are lost as it fuses hydrogen into helium every second. And such that in another 5 billion years, the sun is going to run out of energy as it turns most of that hydrogen into helium and starts to run out of fuel. And the next phase of this lecture, which I'll go a little bit further today, is ways in which we, from afar, view the sun and see that the sun is changing, see solar activity. That includes sunspots, that includes solar flares. So some of the things we see are these spots on the sun's photosphere that when you view them through a filter, right, so that you're not blinded, they look dark. And as we'll discuss, these are caused by intense magnetic fields, which make it difficult for the charged particles of the plasma to exchange energy with their surroundings. Okay, we'll also see and talk about solar flares. This is when there's a region of the sun's surface that is suddenly much brighter. So sunspots are darker and not as hot. Solar flares are much hotter and brighter regions. It's like a giant explosion in the sun's atmosphere, okay, that emits lots of particles into the solar wind. We also get solar prominences. Now, this is like an arc. You'll see these pictures of these like arcs or filaments kind of erupting from the sun's surface. And you'll see that those are actually following like a north pole to a south pole, often that are connected where you see sunspots. And it's like a giant loop of suspended charged particles from plasma trapped in magnetic fields. And actually those solar prominences can kind of explode away from the sun in what's called a coronal mass ejection. And the sun kind of basically burps out huge amounts of charged particles out into the solar wind. Okay, we'll see movies of that. It'll be really neat. So here's sunspots. So up close, and by the way, if you look really close, you see the granules, right? But sunspots can be very large, and you see this furriness, it turns out, are all these charged particles following magnetic field lines. So these sunspots turn out to be regions on the sun's surface corresponding to north or south poles, and you get these magnetic field lines wrapping from a north to a south pole on the sun's surface. And a thing about magnetic field lines is it's very hard for charged particles in these plasmas to move perpendicular to the field lines. They like to follow the field lines. And that makes it difficult for this region that's cooling down to get warmed up by its surroundings. How do we know about the magnetic fields on the sun's surface? Well, we know about magnetic fields on the sun's surface because of a remarkable piece of physics called the Zeeman effect. And we talked about how you can look, you can put the sun's light through a prism. It's called a spectrometer, right? You can see all the rainbow of colors coming out of the sunlight, right? You see how much red there is, how much blue. And remember that you see actually lines of light because the sun produces a spectrum of light that reflects the type of atoms that are in the sun's atmosphere. So you have actually like absorption lines, for example, corresponding to hydrogen and helium. That's how we know what the sun is made of. But the really cool thing is that if there's a magnetic field there, it takes those single absorption lines and it can split them into two. So here you're seeing one. So here's where the line would be. It would be a single line, but it's been split into two here. So, and the degree to which those things split is proportional to how strong the magnetic field line is, or the magnetic field is. So stronger magnetic fields cause a larger splitting in those spectral lines. In that way, we can actually map out the magnetic field along the surface of the sun. So we have a really good idea of the fact that the sun has a lot of things going on when it comes to magnetic fields, very strong magnetic fields on the surface of the sun. And so this is kind of the picture that we see when we talk about sunspots. So here's these darker regions called sunspots. They're about 4,500 degrees Kelvin. Whereas remember, the temperature of the sun is a little bit more than 1,000 degrees hotter on average. Remember, the sunspots are still red hot. They're just a little bit darker than the rest. And what we see is that there are magnetic field lines going from a north to a south pole. Trapped along these field lines are charged particles that can sometimes cause a filament, if you see them. And one thing we're going to talk about next lecture in a lot of detail is the fact that the magnetic field changes on the sun every 11 years. Okay? And this is called the solar cycle. Okay? And so there are times when the magnetic field is such that you don't see very many sunspots, right? We're just coming out of a region now, out of an 11-year cycle, where we're just coming out of the time where there are hardly any sunspots, so we can't see them. And we're entering a region where we're going to start seeing more and more sunspots. Okay. Corresponding, so when we see lots of sunspots, the sun also overall is a little brighter. There's a little bit more flares happening. There's more radio waves from the sun. And this is an example. This is showing from 1975 to 2005, 3 solar cycles. Okay? And all these things are happening at once. You get fewer sunspots, more sunspots, fewer sunspots, more sunspots. The sunlight is a little bit less, a little bit more, a little less, a little more. Fewer solar flares, more solar flares. Fewer solar flares, more solar flares. And all of this is due to the fact that the sun's magnetic field changes every 11 years. And that's what we're going to come back to and talk about when we finish this lecture on Wednesday. Are there any questions before I let you go? All right, well, I will see you on Wednesday.
Thank you, Professor. Thank you.
I had one question. Don't worry.
Yeah, sure.
So like for grades and stuff on D2L, I was looking and I just don't know exactly what
What's up, yo?
like it has all the quizzes, not do all the homework. So is there any way I can calculate the homework and the quizzes together to get my accurate grade?
Yeah, so the quizzes are administered on D2L. So yeah, you get your quiz grades on D2L. And overall, those quizzes are worth 50% of your grade. And then on mastering astronomy, that's where you do your homework, right? There, that'll tell you your mastering astronomy percentage. So you see how you're doing in terms of percent, and that's overall worth 25% of your grade. And then participation is worth the other last 25% of your grade. So you can calculate that yourself just to see where you're at, or you can email me and I can help you. If you want to just email me, I can give you help you calculate that.
Okay, thank you. I was just confused about it because I would go on D2L, I would see the quiz grades, then I would always do my homework and I would see my overall grade with there, and then like participation and stuff, and then I was just confused, so I didn't know if I was like a B, C, like that.
Yeah, why don't you email me and we'll talk.
Okay, thank you.
Bye.